Good afternoon, Sagar. Okay, I wish you the same. How are you? Had a lot of sweets. You have any questions, Sagar? I'm fine. Why is this coming? Good. So, how is it going? Learning inorganic chemistry. Good. Oh, nice. Yeah, I can initiate some discussion provided some more people join. If not many are joining, then probably we can look into something that you need some clarification or something. Many students may have class during this time, I think, 4 to 5. Hmm. Did you learn something new from this course, Sagar? Hi, Yashwant. How are you? Oh, nice. Hmm. I'm happy. Okay, that is the intention. Okay, the intention of offering this course is to make sure that you get something that you normally don't see in in other classes or maybe in textbooks and other things. Namaste, honey. I'm fine. I'm perfectly all right. Good evening. What is that? Kulkem? What is the name? You have any doubts as far as this course is concerned? Okay. How many DD transitions one can anticipate in uh, hexa coordinated copper system? Hexa coordinated copper is a D9 system, right? So D9 system, of course, D9 system. a John-Taylor distortion is there. If the John-Taylor distortion is there, okay, normally D9, I had already explained, in electronic configurations such as D1, D4, D6, and D9 have similar trends. Okay, because D1 is one electron, D4 is one less than half filled, D6 is one more than half filled, D9 is one less than completely filled. So they all, strictly speaking, they should show single DD transition. But whereas in case of your copper compound that you are asking, where four amine groups are there, four ammonia are there, and two water are there, and it's a octahedral compound, and because of John-Taylor distortion, you see more peaks. You are seeing two DD transitions that I have clearly shown in one of the slides. Okay, if you have any doubts further, just go and look into it. It should show two. Okay, in absence of uh, any of these system, in absence of John-Taylor distortion, they are supposed to show one. Is that clear? Whether it's tetragonal compression or tetragonal elongation, they would show two absorptions rather than showing one, okay, as per thumb rule that we follow. Is that right? Can you open that one? I mean, that should be there, I think. So assignment number 7, question number 8, I don't have with me. Just let me dig into it. Yeah, look into assignment number 7, question number 8. I would get back to you. Okay, and thermal stability order of metal complexes. You cannot simply rationalize the thermal stability order of metal complexes unless we define what are the ligands, surrounding ligands. So it can vary, and also it varies upon the oxidation state, and also you are referring to 3D metals, 4D metals, or 5D metals. Okay, it has a lot of parameters when you talk about thermal stability. And usually compounds, if they have organic ligands or organometallic compounds, have less thermal stability. Okay, uh, because they can readily decompose. But again, we have to look into several other aspects. Okay, if you simply ask me thermal stability order of metal complexes, I cannot give. Okay, this the relative stabilities we can only give with respect to whether it's homoleptic or heteroleptic and what kind of ligands are there, and all these parameters should be considered. Okay. Hmm. Okay, the question number 8 is the oxidation state of molybdenum in tropylium molybdenum tricarbonyl cation is. Okay, so just look into it. What is the oxidation state of molybdenum? So tropylium is a cationic, right? It's cationic. So molybdenum is in zero valent state only. So that cation is there. So outer charge is positive. So if outer charge is positive, okay, it should be, uh, you know, uh, yeah, it should be +2 then. What is the answer?
And then outer charge is also +1.
Yeah, inside nothing is there. So inside we don't have any anionic ligands or anything. Okay. So we have MoCO3 and a cationic ligand in the coordination sphere, and outside the bracket we have plus charge. So that plus charge just carries. That way, oxidation state of metal is 0. Okay. And then the oxidation state of uh, molybdenum is 0. That is it. Okay. What did you write? So doubt DOUBT. Okay. 3 plus 3. I mean, what is that one? The correct answer is 3. What is 3 means? 0. 0 oxidation state. Yeah, oxidation state of molybdenum is 0. That is the reason outside the bracket plus is there. Yes, that is correct. Yeah. Yeah, 0 oxidation is correct because positive charge, positive ligand is there, and also bracket outside also, okay, positive charge is there. Tropylium is not neutral ligand. It is cationic ligand. Okay, tropylium is a cationic ligand similar to nitrosyl. No, I already explained about DD transition. Okay, DD transition, very DD transition question here. Oh, you asked that. I told you already answer. Okay, you see two absorptions. Can you open that one?
Some random question. Just asking in general.
No, I know. Yeah, so I already explained to her. Yeah. No, that is also there in one of the slides. Okay, yeah. That is 52, 53 or somewhere. Yeah, DD transition question I already answered, you know. It shows two absorptions. Does it show 3 absorptions? Let me see. I don't think it. I have put the plot for Janta and distortion. Yeah, I will get back to you that in a minute, okay? So tropylium is a cationic ligand. It cannot be neutral ligand, okay? It's in internet. So, hmm. The two, right? It should. No, actually, I think it's incorrect. It should show two only, two absorptions. Okay. Just refer to my which lecture that is? Huh?
14 lecture.
Lecture number 14? Yes. Okay, lecture number 14. Please refer to my lecture number 14. Okay, I have shown you the splitting and also the transition. Okay, it should be two. It cannot be three. Cannot be. Yeah, tropylium cation. Okay. So, and Ajay Kumar's, you see, don't go with Ajay Kumar's inorganic chemistry book. Okay, Ajay Kumar's, he must have written something wrongly by mistake or knowingly or unknowingly. It is cationic, okay. So tropylium, okay, what happens? It's a 7-member cyclic ring. We have 3 double bonds are there, okay, and in order to make it aromatic, right? So it becomes okay cationic, okay. It becomes cationic, okay. It loses 1 electron and then it becomes cationic, okay. So don't go with Ajay Kumar's. If Ajay Kumar says it is a neutral ligand, that's incorrect. Okay. which reference book we should read. Okay, so for assignments, well, if you listen to my lectures, that's good enough. If you want, you should look into housecraft book, okay, and also uh, Shiver and Atkins book, and also Inorganic Chemistry by F.A. Cartner, 6th edition. Yes. Okay. So, and J.D. Lee also, there are plenty of mistakes are there. Please don't refer J.D. Lee and also Ajay Kumar's book. Okay. Unless you know whether something is correct or not. Okay. Maybe the book is cheaper, but you may not get what you want, or you may be, certain things may mislead. Okay. Careful while choosing, textbooks for reading and understanding chemistry. Well, that is the reason it's very difficult. Okay, and of course nowadays tetrahedral reactions are very fast. Okay, and then coming up with kinetics under normal circumstances is difficult. But now we have, okay, methods are available for determination of the rate of a reaction, even if it is much faster. Okay, picosecond reactions also can be measured. We have equipments, okay, instrumentation for measuring rate of the reaction. So it shouldn't be a problem now. Okay, those days, okay, Basello and Pearson book was written in 60s. Okay, 60s means much of this work was carried out in 40s, 30s, 40s, 50s after, okay, after coordination theory was established. Okay, so that time there was limitation. Even NMR was not there. Okay, EPR and all those things were not there. Okay, so but nowadays we have many. Even mass spectrometry can also assist you in understanding. Okay, and there are many instrumental, analytical instruments are there at our disposal for measuring the rate of much faster reactions. Okay, just okay. Then let me look into that Missler and see. Okay, but in general, okay, with the DD antenna distortion is there, there should be two. Okay, and if it is showing three, there may be one shoulder may be there. Okay, then I have to just write uh, Tanube Sugano diagram and look into it. Okay, yeah. Maybe I will look into it and I will get back to you through email. Okay. Well, the practice book is not there. Okay, practice book means basically what you should do is look into the exercise, the problem set given at the end of each chapter in both Shiver and Atkins as well as Housecraft book. So that is good enough. If you answer all the questions, you should be able to answer most of the questions that you come across in competitive exams. Hmm? Hmm. Sagar, you're asking some question about, okay, sir, trans effect, elaborate one more. Trans effect, by definition, you know what it is, right? The labelizing effect of a group trans to itself during substitution reaction. That is called trans effect. How that operates? Okay, so we do not have a single theory to explain trans effect. Basically, we have three well-defined theories to explain depending upon the nature of the ligands that are having trans influence. Okay, so one is like neutral ligands like sigma donor ligands like water and ammonia, and other one is negative ligands like chloride, okay, and bromide, iodide, and other things. And the third one is pi acceptor ligands. So sigma donor, pi donor ligands, pure sigma donors, and sigma donor pi acceptor. So we have three theories. First one is polarization theory. In polarization theory, what happens? Okay, if it is a homoleptic, there shouldn't be any problem. Yeah, I will just write it down. Continue. Where is oh, here it is, right? Yes. Here only, no? This one, right? Yes. Yeah. Okay, so as I said, uh, trans effect, we have one is polarization theory, second one is kinetic electrostatic theory, and third one is pi bonding theory. So I had already explained all those things. So in case of polarization theory, what happens? So if you have mx4, there is no pi, there is no trans effect because all are equivalent. Any at a given time, if you are performing substitution reaction, any one of the group would leave. That means there is a cleavage of one of the mx bond, okay, but doesn't make any difference which one is there. But on the other hand, if you have something like this mx3y, okay, certainly there is a difference in the electronegativity of our donor properties. In that case, what happens? For example, let us assume metal is here, okay, and four ligands are there. So one is here, one is here, one is here, one is here. Okay, so in this case, what happens? Because of this one, they induce, okay, polarization on the metal also. So metal, instead of metal is cation in this case, what happens? Metal is also polarized like this, plus and minus. Okay, metal under the influence of this kind of unsymmetrical ligand field. So in this case, what happens? The stronger one is X is negative, okay, and then here X is X is negative, okay, X is negative, so they will be towards positive one, okay. So on the other hand, what would happen is on the negative side, okay, you have here is let me write here like this. Okay, so if you have here, okay, so if so no, let me write here. Metal is polarized means something like this. Metal is, so in this case, let us say you have polarizability. So now the ligands are negatively charged. So the negative ligand one comes here, okay, and the other one Y. What happens? Y is weaker. It comes here like this. Now basically what happens? The charges are same. As a result, it repels. As a result, what happens when you see this bond is longer and this bond is shorter? So that means now substitution can happen. Okay, this is what happens in case of polarization theory. In kinetic electrostatic theory, I mentioned you should know which group is electron donating, which group is electron accepting. Okay, and if electron rich groups, okay, or anionic ligands are there, you just take something like this. Okay, so for example, you take something like this, okay, and NH3 and NH3. If you take this one, okay, so then in this case, you have to identify which pair is electron repelling and which pair is electron attracting. Okay, based on that one, you can explain kinetic electrostatic theory. Here, a group, trans-directing group, a group opposite to that one, and the incoming will be trigonal planar, other one will be axial. Okay, that here how to consider which one is axial, which one is equatorial, that you should know. More electron donating groups and more electron withdrawing groups. Okay, so which one will go to apical? So based on that one, you can explain kinetic electrostatic theory. In case of pi bonding theory, what happens if the two ligands are there? One is a weak back bonding, one is a strong back bonding, and if they are trans to each other, let us say X and Y, and M is here. Okay, so M orbitals are something like this. Okay, okay, and then if Y is and X is there like this. So in this case, what happens if the X is very strong? Okay, in this case, what happens? It pulls all the electron density, leaving very little electron density for interaction of the Y. So in this case, what happens? The rewritten will be something like this. M. Okay, so now it is interaction is more here, and then here interaction will be with Y, interaction will be very less. Okay, because less electron density is there, automatically it is cleaved. So this is how you can explain trans influence. Okay, in case of neutral ligands, sigma donor, pi donor ligands, and also pi acceptor ligands. Okay. So these things I have given with clear examples, and also I have shown you how this method, especially the second one, you can use it in the generation of trans platin and cis platin. Okay, please go back and look into it. That is in uh, I have forgotten which lecture it is. Okay, you can see that one. Okay, close this.
Stop sharing.
Hmm?
You have to do stop sharing.
How to, yeah, stop share. Okay, you are sharing. So here, okay, okay, now it came because it was stop sharing, right? Oh, yeah. Is that clear now? Of course, you can read. I have given more explanation in my lecture. Okay. Any more questions? Hmm. Here also question can be seen. Right. Oh, here it is, right? Chart. Oh, here. Okay. Here. This one. Oh. What is the structure of bismuth 5? What is that one? Oh, gentile cation. Bismuth 5. Is it bismuth 5? Hmm. Bismuth 5 3 plus. Bismuth 5. Yeah, you can use here Wade's rule. Okay, so let me come back to that one. I will come back to that one along with another. If let me see if any other question is there. A little bit doubt in entering ligand replaces which ligand. Okay, yeah, entering ligand replaces which ligand? The ligand that is weaker. Okay, for example, when we talk about one is chloride, one is iodide or something, or one chloride is one another one, the most electronegative one, in this case, sigma donor one. Okay, that will hold because that will pull positive charge of the metal after polarizing. So that bond will be, like plus and minus is there. Electrostatically, that is more attracting, whereas other end negative is there and ligand is also negative, that will be essentially repelling. So that is the replacing ligand. So that would go, and in its place another ligand will come. Okay. Yes, that is true. The nucleophilicity order is considered in trans effect. Okay, trans effect, all these aspects are considered. Nucleophilicity is there, and that is the reason one theory cannot explain all those things. Okay, we use three theories. In question number assignment 10, question number 3. Okay, lability of the ions towards substitution reactions follows the order. Okay, so lability when it comes, okay, you have to see, of course, here we are all talking about high spin complexes. Okay, we are not talking about low spin complexes. With high spin complexes, if you start writing, okay, you start writing crystal flux separation energy also. Okay, you will understand. For example, here the correct answer is uh,
So A.
A. Huh? So A, if you take, what we have is D4 system. Okay, the first one is D4 system, the second one is D5 system, and third one is D3 system. Okay, then if you look into it, D5 system, okay, little bit more stability is there. Okay, compared to D4 system, right? So it's a high spin complexes, and the lability of the ions towards substitution reaction follows the order. Okay, uh, chromium 2 plus is 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 much more labile, right? Lability is decreasing in this fashion. Okay, lability is decreasing. Chromium is there, and then in case of tungsten, well, these are all again. They should be hexa coordinated compounds here. Hexa coordinated compounds only we are referring. D4 is there, and the D5 is there, and stability is increasing towards chromium. Okay, vanadium is the least stable, and then manganese, and then chromium. Okay, B5. Okay, B5, what you should do is, so for example, P4 is there. You take P4. If you consider P4, uh, I told you, you can just ignore S electrons. Okay, S electrons will go for bonding, and then you consider P electrons. If you consider P electrons, what we have is, in case of P4, 3, 3, 3, 12 electrons are there. 12 electrons means 6 pairs. Okay, right? 6 pairs are there. If 6 pairs are there, okay, that is n plus 1. Okay, n plus 1 6 and n is 5. That is trigonal bipyramidal geometry. That is close out. And if it is n plus 1 is 6 and n is, okay, n plus 1 is 6 and then n is 4, then it will be n minus 2, that n minus 1. Okay, that is called Nido, and then Arachno. So that means basically for P4 to begin with, trigonal bipyramidal geometry you make and remove one vertices. Okay, one vertex if you remove, then it becomes 4 tetrahedral geometry. In the same case, in case of bismuth 5, okay, bismuth 5 we have 15 electrons are there. Out of 15 electrons, you remove 3, you will be having 12 electrons. Okay, when 12 electrons are there means 6 pairs. 6 pairs is n plus 1. N plus 1 is 6 and n is 5. So it is trigonal bipyramidal geometry. Okay, bismuth has trigonal bipyramidal geometry, right? So that is the answer. You got it, honey? So for bismuth 5, 3 plus, 5 into 3, 15, 15 minus 3 plus charge, 12. 12 is 6 pairs. So that is your skeleton electron pair. Okay, that is n plus 1 is 6, then n should be 5, is closure structure. So you have 5 bismuths are there, 5 closure structure, and the geometry is trigonal bipyramidal. Is that clear? What is the magnetic moment of L? You have to calculate that one. That is, what is OAC? Copper acetate. Okay. No, copper acetate. Okay. Copper acetate. What is the nature of acetate ligand here? What is the nature means? All acetate ions are anionic. Okay. Our acetates are anionic. And simply if you show 2 copper atoms are there and 4 ligands are there. Okay, so the 4 ligands will be something like this. One acetate, 2 coppers are there. You assume 1 copper is here and 1 copper is here. Okay, 2 acetates are bridging. in this fashion, another acetate comes here and another acetate comes here. Okay, so right, so this is 2 copper and this is 1 acetate bridging with C double bond O and then O minus, and then another one comes like this. Okay, and then one more is coming like this, one more is coming like this. This is how the copper acetate structure looks like that. Okay, and well, acetate is a weak field ligand. Okay, because O minus is there and then oxygen is a hard center. Okay, weak field ligand that is, but chelation adds some stability. Okay, and then magnetic moment you have to calculate. For the magnetic moment it's a D9 system. Okay, simply calculate it. Okay. Yes, main group chemistry, all cations, clusters, you should be able to tell. Even P4, you should be able to tell what the geometry is, right? So you keep looking into, solving, and you will become, professional in using Wade's rule for many things. Okay, I didn't have time. I don't know. I'm not sure whether I discussed metal carbonyls also. Did I discuss metal carbonyls? Okay, metal carbonyls, we have to make several assumptions. Okay, if you take metal clusters, carbonyl clusters also, we can use very nicely Wade's rule. You want me to wear necktie? What is important is what I say about chemistry, not necktie. Okay. Oh, you wanted to see my periodic table necktie? Good. You can also buy one. What is the reason behind it? I say, very interesting question. Okay. So I'm a chemistry person. If I find something chemistry, I have a periodic table is there. I have all the samples of elements with me. Okay, I have a periodic table pad is there, and I have a periodic table chart is there. Yes, I mean in chemistry, I should have those things, right? I keep it. Okay. For example, if you see something, you also buy, like, so it's periodic table. I like it. Okay. What is it? I'm not telling what you say. So you are making some analogy. So you all like my tie? Good. I haven't decided anything about next course. You're all anxious to, listen to my next talk, or looking forward for my next talk, next lecture series. Certainly I will do it. Certainly I will do it. I may come up with a new edition of my main group chemistry. Okay, so I can add more instrument, more details into that one to make it better. Well, I think about UV visible spectroscopy, and that includes DD transition, all those things. There are some courses already, I believe. Okay, I don't want to repeat because some of my colleagues from maybe from IIT or other IIT are already offering, I think. Well, let me see. in what context I should bring all those things. I might float another course on interpretive molecular spectroscopy. In that one, okay, I think I'll be having enough time to incorporate whatever you're asking for it with more detail and more examples. Okay, certainly. Okay, let me do that. Okay, if it is, you know, teaching something, okay, and you people are learning something from a course, I would be more than happy to offer more courses in the years to come. Okay. So another week is left for completion of the course, and focus on reading textbooks. Okay, and try to answer all the try to solve all the problems. Okay, given at the end of each chapter. So that would make you familiar. If you learn chemistry through problem, chemistry is not a problem at all. Okay, if somebody gets 90 plus, that's really good. Okay, then you should buy a tie for yourself. Okay, and say I'm a proud chemist or something like that. Well, in last week, I think some NMR and IR are there, I believe. Okay. Uh, hmm? UV visible is there. Yeah, UV visible has started, I think, right? Yes. Yeah, UV visible is there. Okay, UV spectroscopy is there. Little bit of UV spectroscopy is there, and then NMR is there, and also IR is there. Okay, but not in detail, but in brief. Yeah, so UV visible, NMR are there, and also one lecture includes IR spectroscopy also. Okay. Quite interesting. You come across many examples of okay NMR related to multinuclear NMR. Okay, and a couple of examples are discussed with respect to IR and also UV visible. Okay. So if there are no more questions, okay, see you all. Okay, in another week course will be completed, and I'm sure you're all taking exam, right? It gives a good experience for you people to answer other questions. Okay, answer carefully. Okay, give some thought. Simply do not, try to work out and answer the questions. You should be able to answer the questions. Okay, get good grades and feel happy about that. So Rajasthan, yeah, I visited Jaipur a few times. Certainly next time when I come, okay, I would inform you. Okay. If you are visiting Mumbai, you can always come and see our department. You are most welcome to come and visit our chemistry department, IIT Bombay. Okay then, huh? Okay, so okay, see you all. I wish you all the very best. Okay, stay safe and take care. Certainly, I would inform. Okay. Okay then. See you all. Okay.